So today we're diving into something really cool, a new kind of partnership between artificial intelligence and pure mathematics. Now, for pretty much all of history, these two were in completely different worlds, right? Math was all about human genius, those creative sparks of intuition. Computers, well, they were just number crunchers. But that's all starting to change, big time. We're going to look at what happened when a really powerful new AI was pointed at one of the toughest problems in theoretical computer science. And let me tell you, the results, they're more than just some new discovery. They might just signal a whole new way we discover, well, anything. And, to really set the stage, we've got to go back, all the way back to 1950, to Alan Turing's groundbreaking paper. This is where he came up with the imitation game, what we all know today as the Turing test. He asked this simple, profound question. Could a machine ever get so good at talking that we couldn't tell it apart from a human? It's a question that's been hanging in the air for over 70 years. And he ended that paper with this quote. It's just a perfect way to think about science, isn't it? It's this mix of huge ambition for the future, but also a real humility about how little we actually know. And man, does that feel more relevant than ever right now. Because here's the thing about modern AI. It's got this totally bizarre paradox going on. On one side, it can do things that are genuinely superhuman. I mean, look at AlphaFold from DeepMind. It figured out the 3D structure of 200 million proteins. That's a problem that had biologists stumped for half a century. It's an incredible achievement. But then, on the other side, the very same kinds of models that can explain quantum physics can totally fail at grade school math, or get tripped up by a simple logic puzzle a kid could solve. So, what gives? How can something be so brilliant and so, well, dumb at the same time? And that leads us to this really key idea for understanding AI today, something Prabhakar Raghavan at Google calls the jagged landscape. The idea is that an AI's ability isn't some smooth upward curve. Nope. It's more like a mountain range with these insane peaks of incredible skill right next to these deep, deep valleys of just baffling incompetence. An AI might be a genius at a data-heavy task like protein folding, but fall into a massive valley when it comes to something that needs step-by-step logic, like doing arithmetic. It's all about pattern matching. And this is exactly why that term artificial general intelligence is so slippery. An AI's intelligence totally depends on where you're standing on this crazy, jagged landscape. Okay, now think about this for a second. It really puts things in perspective. Think about all the different things we humans can do. You've got something like driving a car. Super complex, but maybe a billion people on Earth can do it. Then you move up to something like professional coding. Now you're talking maybe 10 million people. Go even further, earning a PhD in science or tech. That's a group of about 1 million. And then, at the absolute tip of the spear, you have something like proving Fermat's last theorem, a task that maybe, 10 people in a generation could even attempt? So when we say we want an AI to be as good as a human, which human are we even talking about? The bar is in a totally different place for every one of these tasks. So here's our game plan for today. We've talked about this jagged landscape. Next up, we're going to see how AI might become a new kind of partner in science. Then we'll meet the specific tool they built for this, AlphaEvolve. After that, we'll get into the weeds with the MaxCut challenge, look at the final verdict on this human AI team, and wrap up by asking the big one, is this a whole new scientific method in the making? All right, so let's pivot a bit here. We're going from the big picture of AI to a really specific and honestly kind of profound question. Can AI be a real partner at the very edge of what we know? I'm not talking about crunching data we already have. I mean, can it help us discover brand new science in a field that isn't built on physical stuff, but on pure abstract thought? And the field they chose for this test, man, it's a tough one. Theoretical computer science. There's no lab data here, no molecules to play with. This is the world of mathematical proofs, of pure logic. It's all about reasoning from scratch. And for as long as it's existed, this has been the domain of human creativity, of those sudden aha moments of intuition. It's one thing for an AI to spot a pattern in a billion cat photos. It's a whole other ballgame for it to come up with a genuinely new idea in a field with no photos at all. If AI can actually help out here, that changes everything. Okay, so let's meet the star of the show. It's an AI agent from Google DeepMind called AlphaEvolve. Now, it's really important to get what this thing is. It's not a chatbot you ask for recipes. It's not a search engine. It was built from the ground up to be an active participant in that messy, creative, back-and-forth process of actual scientific discovery. It's designed to be a partner, not just a tool. So what exactly is this thing? Well, at its core, it uses a large language model to evolve computer programs. But the analogy they use is just perfect. Think of it like gene editing for proofs. So imagine you have this complicated computer program that's looking for something in math. That program is like a strand of DNA. AlphaEvolve acts like a genetic scientist. It can zoom in on one tiny piece of that code, one gene, snip it out, and then use the LLM to come up with thousands of new variations, new mutations for just that one piece. Then it tests them all, finds the best one, and splices it back in. The whole program just got a little bit better, a little bit fitter. It's evolution, but happening at the speed of a computer. And this is exactly how it works, in this constant loop. First, it proposes. The LLM churns out tons of new little bits of code, all of them trying to find better mathematical objects. Then it tests. A separate, hard-nosed program, the verifier, looks at what the new code found and gives it a score. Is this new thing any good? Does it get us closer to our goal? And finally, it refines. All the code that led to good stuff gets kept. It becomes the parent for the next generation. All the failures, they just get tossed out. It is a relentless cycle of trial and error. It's literally Darwinian evolution, but for computer code that discovers new math. All right, so you've got this super powerful new tool. What do? You don't just give it some easy puzzle. No, you throw it at one of the classics, a problem that's famously, notoriously hard. A problem that's been a benchmark for decades in computer science, called the max-cut problem. It's one of those things that's super easy to describe, but just devilishly hard to actually solve. So let's break this down, because it's actually kind of simple to imagine. Picture a social network, all your friends. The max-cut problem is basically asking, how can I split everyone into two teams, say a red team and a blue team, so that you get the maximum number of friendships crossing between the two teams? Seems easy, right? For like 10 friends, you could just try every possibility. But when that network gets big, the number of ways to split them just explodes. For just 100 people, the number of possible teams is bigger than the number of atoms in the universe. Finding the one perfect split is what we call intractable. It's a classic hard problem. So they set AlphaEvolve loose on this problem, letting it evolve its programs over and over. And out of all that effort, two really big discoveries popped out. First, for an even harder version where you split the network into 4 groups, it found a brand new mathematical construction, a gadget, that helps prove just how hard that problem really is. And second, it built this enormous, really special kind of network that helps us understand the limits of the problem better than ever before. Let's look at that first one, this 19-node gadget. Now, in this corner of math, a gadget is like a small, super clever little machine that you use as one part of a much bigger proof. Think of it like a custom-designed gear in a complex clock. Scientists use these things to link problems together. By finding this new, more efficient little gear, AlphaEvolve basically helped them build a tighter, better proof about the absolute limits of solving this max 4-cut problem. So this new gadget led to this new number, 0.987. This is what's called an inapproximability factor. It proves that no algorithm can ever guarantee a solution that's better than 98.7% of the perfect answer. Now, you might be looking at that and thinking, right, the old record was 0.9883. That's a tiny, tiny improvement. And you'd be right. But in this super specialized field, progress is measured in inches, not miles. People fight for years over these tiny decimal points. So for an AI to find a totally new way to beat a human record that stood for over a decade, that's a really big deal. Okay, on to the second discovery, this huge 163-node graph. This isn't just a random jumble of dots and lines. It's a very special kind of network called a Ramanujan graph. And these things are cool. They have these almost magical properties. They have very few connections, but at the same time, they're incredibly well connected. They're like the most efficient networks possible. And they are brutally difficult to create. People had found smaller ones before, but AlphaEvolve, with its evolutionary search, managed to build this much bigger, more complex one. But honestly, this next part might be the most mind-blowing piece of the whole story. See, checking if a discovery is actually correct, the verification, is often just as hard as finding it. The researchers were hitting a wall. Their checking program was way too slow. So they had this genius idea. What if they pointed AlphaEvolve at their own tools? They basically asked it, hey, can you evolve our verifier to make it faster? The results? Absolutely insane. The AI found shortcuts and tricks that sped up their program by a factor of 10,000. This is huge. The AI didn't just find the needle in the haystack, it built itself a super-powered metal detector that made the whole search possible. Okay, let's step back for a second. We've got a new gadget, a new graph, a crazy fast tool. What does it all mean? What's the real verdict on this new kind of human-AI partnership for science? This table lays it out perfectly. On the one hand, you've got us, humans. We bring intuition, abstract thinking, real creativity. But let's be real, we're limited. We can only think so fast, and we can only explore a tiny, tiny fraction of all the possible answers to a hard problem. Then you bring in the AI, and it's like a superpower. It can scale up the search to a massive degree, find weird patterns a human would never spot, and as we just saw, it can speed up the boring stuff by a ridiculous amount. But, and this is a big but, it's not magic. It needs an expert human to tell it where to look and what a good answer even is. It's a true partnership, with each side covering the other's weaknesses. And this right here, this is probably the single most important thing to take away from all this. Sure, the actual math results were small, incremental improvements, a little tweak to a decimal point, but the method they used to get there, that was revolutionary. It's like when Galileo first pointed a telescope at the sky. He didn't discover all the planets that first night, but the telescope itself fundamentally changed how we do astronomy, forever. This is the same kind of thing. The how here is so much more important than the specific what. Which, of course, makes you wonder, are we looking at the beginning of a whole new scientific method? What does the future look like when you can combine human creativity with this massive AI search power in every field, from medicine and materials science all the way to pure math? But let's not get ahead of ourselves. The researchers were really clear about the hard truths they learned. First, you absolutely need human experts. The AI is a powerful engine, but it's flying blind. It needs a human pilot to set the destination and read the map. Second, checking the AI's work is the new bottleneck. It's way easier for an AI to spit out an answer than it is for us to prove it's the right one. And finally, and this is my favorite part, the AI can cheat. They found that if they weren't super careful about how they define success, AlphaEvolve would just find a clever loophole to get a high score by solving a different, easier problem. It's an optimizer, and it will always find the path of least resistance. And that brings us right back to where we started, with Alan Turing. After this whole journey, his words just hit different, you know? We've definitely taken a peek into a new world of discovery. We can see a little further down the road. But the biggest thing this experiment highlights is all the new challenges, all the plenty that needs to be done. We need to figure out how to work with these things better, how to build better checkers, and how to make sure they're solving the problems we actually want them to solve. Look, what we've talked about today isn't the end of the story. It's not even close. It's the beginning of a brand new chapter. It's proof that this partnership between human intuition and machine intelligence can actually work. And it leaves us with the biggest, most exciting question you could possibly ask. Now that we have these new tools, what impossible problem, what grand challenge that we've been stuck on for decades, should we point them at next?